Okay, very good morning. First, on behalf of my center, CEDEC, and my universities, I would like to thank you to organizers to invite us, I mean to invite our students to join that competition. So for the IC design competitions. And on behalf of my centers and my universities, SM, we also really appreciate and thank you to TSRI and TSMC. They approve our applications to be the part of the join in a program under University FinFed program. So with that program, so we just done the NDA the last year on the October. So that good for our students. That means to explore on the FinFed, the 16 nanometer process to explore in IC design activities. So today my title will be the hybrid lab on printed circuit board, the integration with a CMOS Potentiostat chip for the infection disease diagnostics. So before I go to my talk, so give me a quick overview about my centers. So then I will explain. Then I will elaborate one of part of our current research in the developments, the lab on a chip, but the lab on a PCB. For like now we are working for the Malaysia more like the typhoid fever, the salmonella, and also for the COVID test, the COVID detections. So that I will summarize my talk. So that our university just location in Penang State. So we have a direct flight from Penang to Taiwan, just 4 hours 30 minutes. So by the China Airlines, so that can be the direct flights, just 4 hours, right? So that's what our main campus. So this our first bridge, the Penang first bridge. So when you across the bridge, and then you can see that our campus, and then from campus about the 5 minutes, and then you can reach at our centers. We call the collaborative microelectronic design excellence centers. So we one of the center of excellence under Senate University Sains Malaysia. So this location we call as a sign at USM. So how we have a few the incubation centers. We have a few startup companies. So for example, we have a local company like Opstar Skychip, I mean for the fabless design. So and then we bridging between the academia and the industry to foster the activities in IC design. So from our centers to Penang International Airport, just 10 minutes is very near. So please, so if you have chance, please come and visit us at the Penang Island. So that the nearby the beautiful beach lah. Okay, so that what the role of our centers because in Malaysia, so for the East universities to own their EDA2 is not affordable. It's a very expensive. So the how we did, so for in our centers, so we provide sharing EDA2s to all universities in Malaysia. So from the synopsis, so front end and the back end, and also from a guidance and also a mentor. So we get them to access to our server based on the scheduling. So that we provide the based on the scheduling. So that can access for the teaching and learning, and also for the R&D activities. So in terms of this, we also have the collaborations with our so for fundraise. Before we had opportunity to sign with the TSRI and with through the ADFP program, we only rely on our local fundraise. So how we have the Silterra, so that only provide for the up to 110 nanometer CMOS planar process. So how from that, so that what our centers, so we be under USM and also appointed under Minister of Higher Education. So one of the national top centers to all universities. I mean to give the access for the form design, and then they will link up with our national the local foundries, and then that we do the testing and packaging. So in terms of our research, so in our group, actually we mainly focus on AI-based devices. So to focus on AI-based devices, so in our group, so we have a two main group. So we have the IC design group, how they are focused on the analog design. So we have the group that focus on the chip transceiver design, 5G and 6Gs, and also we have a small group that focus on the digital, and they mean for the ASIC design. So the last years we try to make the recruitment to up more digital to join our centers, because our center we started as an analog group. So there so the last 2 years we try to expand from analog and also have the group that focus on the digital and ASIC, and we have that how the one we design the circuit, so that we have a group that focus on sensors development. So one of the sensor we focus on electrochemical sensing, and also with the MEMS for the acoustic, for the piezo micro machine ultrasonic transducers. So that means how we do the integrations. So the sensors and the chip on what we call the hybridly integrated. So mean the sensors we have on the silicon technologies, and also we work on the printed circuit board technologies, the how we various type of the substrate on PCB, and also on the TPU, Teflon polyurethane, and also on the polyvinyl alcohol, and then we do the integrations for the flexible and the wearable application. And recently, due to the advancements in the advanced packaging, and then recently Malaysia, they got a lot of the investors, and some also from the Taiwan, like the Amcor, the ASEs, how they do the investment in Malaysia. So that how we are instructed by our national government and how to support also in the advanced packaging. So right now we create a small group just focus on the miniaturization of the RDL, the redistribution layer designed to support for the high density interconnect application. So that what we have we have the Silterra, but the last years we just recently signed NDA with DSI. So that how we are started to explore on the 16nm process for us to do the design. So that's why I really appreciate. So from that to approve our application to join is under for the University FinFET program. So that what the few chip that we done in our group. So we have for the transceivers, power management, and also the high voltage drivers, and some digital we started. So we just started with the Silterra, so that we are going to have our new. So we just secure the national fund grant. So how towards to the apply on for the TSMC on the 16nm PDK. So that what we have some. So one we have the sensors. That means how we do our chipset, and then we do the integration. So on the so that the TPU, the Teflon polyurethane, and also we work together with the chemistries. That means they do some chemical formulation to us in terms of the conductivity based on our specifications. And also some that we also work on the flexible coil. So that what we have do. So the ink was provided by our partner from CMOS. They do the graphene ink formulation, and then we printed on the TPU the Teflon polyurethane, and then we integrate with our developed chip, and then we just tested. So one we wrap on the wrapping. So that the food wrapping, and then we put our antenna, the coil, and the chipset on the food wrapping, and then they can use the NFC tap, and then we know what now we just employ the temperature sensors. So the one you tap to the handphone, so they not only provide the power to harvest the harvest the chip, but at the same time also to provide the data in terms of the temperatures value of that that environment. So, but for today, what I'm going to present, so how we cover development on the lab on printed circuit board. So how we do the integration for the biosensors and the CMOS Potentiostat chip. So that can be my presentation. Okay, so for so the one we talk about the biosensors. So we need a small chip. That means the small biosensors. How we miniaturize. I mean all the lab apparatus. So right now, so if we have the infection, and then we go to the hospital, and then we get our blood samples, and then they do the testing, and then some apparatus is too big. I mean they need the use of the blood sample. I mean to get the result. So how we did the one of the technique how we be able to miniaturize as a lab apparatus on the one chip. So that's why we call the lab on a chip. So the on chip they have a function as a lab. They have a function as how to how to do the detection, and then they has a function how to do the mixers. They can do the mixing between the patient sample and the catalyst. So when they do the mixing, and then they be able to do the detection. So some the issue, the one they do the detection. So that means how we be able to convert any the electrochemical phenomenon to the real world. So the how we be able to convert any the biological phenomenon to the real world. So that's why the one of the methods. So the one they do here they will do the detection, and then the biological signal we converted to the electrical in terms of our sensor. In terms of current. So that can be towards to the digital. So that's what that for right now in our case. So how we develop all the functions that on the various type of the substrate we using the FR4. That means the PCB. We also do the applications on the flexible and on the stretchable substrate like I shown just now from my previous slide. So towards to the what we call the lab on the chip or lab on the printed circuit board application. So one of the method that we did in our group. So we focus on the electrochemical sensing principle. So what is the electrochemical sensing principle? So that what the current technique. They have the bulky of the electrode. They have the counter electrode, working electrodes, and also the reference electrode. So how we be able to convert on the 3 electrodes towards to the on-chip type of the electrode. So then the one we do the converted to that electrode. So the on-chip. So how we be able to tap the signal that from that electrode. So that can do the amplification and convert to the digital. So the one of our technique, so they have a lot of the electrochemical sensing principle. Either they use the square wave water metric, or some use the differential pulse water metric. So what we did, so that what we have developed on our printed circuit board. So that means on the back side, on back side of that electrode, we developed the microcontrollers, and also the amplification chip. So the one they have the detection. So actually that blood so that we have the working electrode. So that the counter electrode, that the reference electrode. So all the reaction we created at the working electrode, and then we change the changing of the reduction, mean the oxidation and the reduction current. So from the detection of the reduction and the oxidation current, so mean we need the circuitries, do the amplification and towards to be the digital. So that what the so we have a group that mean we focus on the Vout, that mean the biosensing interface, and also the how we do for the power management unit integrated circuit. So that's why the one of the that what we have a focus first on the sensors development. So right now, so we working so that the zoom of our the electrode type, how we have the U shape, and then that our working electrode, so that the reference electrode. So that means to modify, that means to ensure the, so first we have to ensure that they can provide the signal. So that means to provide the signal, because the current, so this is a concept like the resistance. So as an example, so that your the surface area of your working electrode. So the one we have the probing, so that what one of our probe. So when we have a probe, mean they will disturb the area of the electrode. So when they disturb the area of the electrode, mean they will effect of the resistivity. That mean the resistance. So the one we have, then we drop the sample of the patient. So if sample of the patient they met, for example, that they have the COVID or they have the salmonella, so that means that single that we do a binding. So when they have a binding here, mean they have a match. When they have a binding, when they have a match, mean they will disturb. They mean they will reduce the surface area of the electrode. So mean they will change. They mean they have a more higher. That mean they can have more higher resistance lah. So mean they can less of the current. So okay. So that what so from here, so we have do the integration. I mean all our the design, and then with the microfluidic and all that how we upload with the, so that means the chip. So we do the integration with the microcontrollers. So that how we did for the circuit design. So I mean that what we from the working electrode. I mean we have a current, and then they do the amplification. So that from the working electrode. So that what we have some potential block that we have a design for, because we have to do the amplifications of the current signal. So that how we do. Right now we are working a design on the 180 nanometer process technologies. So that we have some layout, and also some we had the detection on the DPV. So that how we call the differential pulse-voltammetric signal from the sensors. And that what we have the power management unit ICs. So we have designed the LDO and the rectifiers, the bandgap references, I mean to power up the sensor. So that what we have the full system. Then we do the integration that we have. We work together with one of the partner in industries. Mean to develop, mean to plug our chip on the, to develop the one out of the reader lah. So what we have some tested of the equipment that we see. So like because the concept like the resistance. So that way we have the signal. So that we have the abthermal. So when they have a patient of sample, so it means we can see they have the reduction of the current. So that how we do the detection. So that can be the abthermal without binding. So when they have a binding, mean they can reduce the peak of current. So that can be one of the detection method. So that what we have the latest we have about the 0.137 nanogram per microliters. So what we have published on the analytical method for our lab on the chip. So that how we have some. So it means, so when they have the detection, mean they increase the impedance. That mean the impedance behaviors. Mean they have the detection. So how we can do a tested for our few the negative sample and then positive sample, and I mean we can see they have be able to differentiate between the probe and also the negative and positive sample. So and then that what we do the publish recently, so that how we can get about the 7.6 times 10 minus 9 molar per liters. And so then we also tested for the COVID. So what we have our sensors, so we can see, so one they have the detection with a COVID, mean they have a more impedance, so that can be have a highest lah. That means they have the higher impedance. So one of the method that we develop right now, that we be able to detect COVID even though have the one mismatch, that we publish on the paper, the Lab-on-PCB journal. So that we do the publications. So that we have about 0.50 micrometers. I mean the one copy, even though one copy be able to do detection. So I mean we using the circuit mean to amplify. I mean even though they have the lower concentration, but having the amplifier a circuit, that we be able to have a highest of the. So some with so I will skip. So okay, sorry. So that what we have some so that we do some aptamer. So that what we did the sensors. Then we do the integration with the microfluidics. That we be able to do the detections on the real time. That what we develop the IoT, the microcontrollers. So actually, as a summarize my talk today, so actually that we prove some implementations of the different type. So our proof implementation of the sensors. So how we develop on the various type of the substrate. Then we do the integration with the CMOS without circuit to amplify the signal, even though they have the limit how the light concentrations. So we prove for the DNA base, the aptamer. So what be the next step is, so right now we only have do the detection. So the next step we going to have the new funded grant. So how be able to do the integration with the ASIC, mean they do some to add the implementation of the AI, I mean the machine learning. I mean they not only do detection, but ever can do the predictions. That's why we work out with next project with the 16 nanometers. So how to have the memory and then machine learning to learn the behavior of the community in the disease infection. So that what we have our team for the electrochemical team. That means that we have a Prof. Marvati to provide us any the ink development for the graphene and also for the chitosan. So that what our team for my team for a CMOS sensors. We have our collaborator from the Japan and also from CVIM and also from the MEMOS. With that, thank you.
Thank you very much Professor Park. So maybe we can have one or two questions from the audience. Any question?
Yes.
Thank you, Professor Manaf, for the great talk. I just checked my email. In fact, I visited your university in 2018. At that time, I'm serving as the external examiner. I just checked it. So.
Okay. Under your project. That means my previous directors. And then you be one of my external examiner for our students. Yes, for a CEDEC. So that's why.
And right after that, I and Professor Inwei John, at a
Inway.
publication. Inway. Yeah.
Oh yeah, that my foremost professor teach me the electromagnetic.
Oh
Yeah.
So yeah, it's great to see that in the past 6 years, you have a great progress, on the biosensor. Yeah. So I just have a question, on the because you mentioned that it's mainly for RT PCR.
Yeah.
So how about the thermocycle for the amplification?
Okay, so
is it integrated
yes,
with the
yes,
system?
yes. So right now, the what we are working with, so that's the why we use the PCB. So on the back side, we're going to integrate with the heaters. So they can be the isothermal. That mean the only a single heater, so that can do the amplifications.
I see. So you also use the lamp,
Yeah. So we have a D-lamp. So right now we try to remove the concept of D-lamp, but we do so that's why if I see the second slide on the back side, not only the sensor but also we going to integrate with the single heaters. So with a 65 degree. So how we need the microcontroller to make sure the stabilize of the heaters temperatures. Yeah.
So in the near future, you are going to consider use the semiconductor technology.
Yeah.
Okay,
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 thank you.
Thank you very much for the presentation of the professor again. Okay, thank you.
Okay, now is our coffee break time. So next, we are welcome our third speaker, Dr. Jaga Regendan from the Collaborative Microelectronic Design Excellence Center, Universiti Sains, Malaysia. Welcome.